Hey, local linear approximation. This stuff is easy. The directions can be a little confusing sometimes, especially when the book likes to start saying, like, refer to Formula 1 and stuff like that. So let me just make sure we understand here. How do you write the equation for a tangent line? This is in your notes. I'm just going to remind you here for tangent line to some function f of x at x equals. Our book loves to do the x sub 0 thing. That's fine. That just means some like particular x value. I'm going to say at x equals c, kind of like what we did back in the limit days. I'm going to call it c, but they like to say x sub 0, so whatever. It just means some fixed point that we would like to remain generic so we can make up little recipes for things, formulas, and whatnot. So to write the equation for a line in point-slope form, we need a point and we need the slope. So here's the point. The point is just x, sorry, not x, c. The point is c. That's my x value, comma, f of c. Right? You plug in c, you get f of c. And the slope, well, now that we have calculus notation, we have, we call that f prime of c, right? It's the derivative of f at that point c. So the tangent line equation is y minus y equals the slope times x minus x. And since we're going to be actually using these tangent lines to find y values, you could write that as y equals f of c plus f prime of c times x minus c. This is just the equation for a line. So let me just flip back in the book here. So what do they give as their Formula 1? Yeah, it's that. It's exactly that, except they wrote they wrote x sub zeros. And instead of writing y equals, they're writing that as long as you stay close, as long as you've got x values that are pretty close to c, then f of c should be approximately equal to this. It's a good approximation. F of some x value for x values that are close to c. Right? Closer you are, the better you could expect your approximation is going to be. So that's all they mean there. So what we want to do is just find the tangent line. We just want to do it. So 1a, use Formula 1 to obtain the local linear approximation of x cubed at x sub 0 equals 1. In other words, find the tangent line to this at this. So what do I need? Well, I'm going to need the derivative. And I'm going to need a point. So I plug that in there and get the point 1, 1. So what is my tangent line? It's y minus 1 equals y prime of 1, when I plug 1 in here, is 3, slope times x minus 1. If you're still not on the point slope thing, I'm sorry, this is the end. It's the end of the road for you and your y equals mx plus b shenanigans. It's time to do it this way. I'm going to move that over to that side. So there we go. I'm not going to fuss at you if you don't move this, but for the purposes of actually using this, it might be a little better to have that on the other side. And B, use the formula to rewrite the approximation in terms of delta x. Okay, what does that mean? Well, if we're going to plug something in, we're going to plug something in that's close to x. This is my fixed x value, and this is my variable x value. So the difference between these is actually the delta x. And if you want to kind of try to understand on a more intuitive level what is going on here, what we're saying is that the y value, if you're thinking about this as a local linear approximation, not just a tangent line, what we're saying is, what's the y value going to be? Well, it's going to be 1, but it's going to be a little bit off from 1. And how much off is it going to be? Well, this is the slope, right? That's like the steepness of it. So as much as you kind of wiggle back and forth this way from that x value, the slope dictates how much it is going to wiggle up and down, right? So however much you wiggle back and forth, it's going to be like the slope times that is how much it's going to wiggle in this direction, right? I think that's a good way to think about it, if that makes sense to you. So that's all they mean there. And for C, they want us to use this result to approximate and then confirm that the formula obtained in part B produces the same result. So of course it's going to do the same thing, because the delta x between 1.02 and 1, because that's where I was approximating from, right? This is that, it's like how far away is 0.02, and when I plug it in here. So I'm going to get the same thing either way. These formulas are identical. So my delta x is 0.02, so that means that 1.02 cubed is approximately equal to, according to this, 1 plus 3 times the difference between these, or delta x, whichever way you're thinking about it. So 3 times 0.02 is 0.06 plus the 1. Right? That's how you do a local linear approximation. Want to see if it was good or not? Not too shabby. All right. That's what the game is here. If you looked at these problems and you were a little confused about what you were supposed to be doing, that was part C, by the way, then you should pause this video right now and try another one of them. Go ahead and try number 2, and then just come back here and compare in a second. What is number 2? Same deal, but we're doing now y equals 1 over x at x sub 0 is equal to 2. Okay, so let's see, y prime is equal to, that's x to the negative 1, so that's negative x to the negative 2. And the point, when I plug 2 in here, talking about the point 1, sorry, the point 2, comma 1/2. So my tangent line is y minus 1/2 equals the slope. When I plug the slope in here, y prime of 2 is 2 to the negative, 2 squared is 4. The negative sign flips it over 1/4, and that makes it negative. Negative 1/4. Times x minus 2. And that's the answer for part A. You could move the 1/2 over. And then for part B, they're just saying, hey, we want you to recognize that this is just like a how far away are you from the x value where you made the tangent line. So you could call that like a delta x. And then in part C, I think that's what? Isn't that what part B? Yes. And then part C, what about if you do it at 2.0, 1 over 2.05? Well, the delta x would be 0.05 then. So that would be our f of 2.05 would be approximately equal to 1/2 minus 1/4 times 0.05, which is 1/20th. Right? Whether you do 2.05 plugged in here and then get the 0.05, or you just go right to here, like it's 0.05, that's what the delta x is. That's what is happening. So I guess it's 1/2 minus 1/80th, so it's 40, so 39/80ths. Maybe you used your calculator. Let's see. Let's compare. So 1 over 2.05 is that, and 39 over 80 is that. Not too shabby of an approximation. All right. Let me just pause for a second and say, so why would anybody want to do this kind of approximation? Well, if you think about what's going on here, the two choices are either do 1 divided by 2.05, which is not a super fun division problem. You could try it if you want by hand, or do this. I would argue that this is way easier to do by hand than that is. Of course, we have calculators, so there's that. And that would be a fair objection. But there are reasons that we like to have these approximations. And this is, I mean, this is early days for us in calculus, so this is like approximations light. It's going to get heavier down the road. All right, numbers 3 and 4, same kind of idea. We've got the f of x is equal to the square root 1 plus x. So f prime of x is equal to, that's that to the 1/2, so that's 1/2 1 plus x to the negative 1/2 times the derivative of what's inside, but that's just 1, so that's good. And we want to find the tangent line at x sub 0 is equal to 0. Okay? So when I plug 0 in, my point is 0, 1. And my slope is, I plug 0 in here, that's 1, is 1/2. So f prime of 0 is 1/2. Okay? So what's the tangent line approximation? For values around 0, that my tangent line approximation is going to be y is equal to the y value plus the slope times delta x, which is x minus 0 in this case. Right? That is the tangent line. And they want us to use it to approximate the square root of 0.9 and the square root of 1.1. So the square root of 0.9, notice here that if you want this function to do the square root of 0.9, the thing that you have to plug in here is negative 0.1, right? Because this already does 1 plus something. So you'd actually have to plug in negative 0.1 to get that to do the right thing. And that's going to be approximately equal to, right here, 1 plus 1/2 times the x value, negative 0.1. That's 0.5, so that's going to be 0.95, I believe. All right, and then f of positive 0.1 is going to add a 0.1, and that's approximately equal to 1 plus 1/2 times positive 0.1, which is 1.05. Graph f and its tangent line together and use the graphs to illustrate the relationship between the exact values and the approximations of those things. Okay, sure. Let's see. If you kind of skipped over this, that's okay. But I want to show you what they have in mind here. So let's graph the actual function here, the square root of 1 plus x. And then let's graph the tangent line, which is y equals 1 plus 1/2 x. And let's just go ahead and zoom 6. Look at it on the regular window. This is not a good window to look at it on. My graph, if you're wondering why my graph or my calculator graphed it that way, I am in simultaneous mode. Yours might be in sequential mode. That means sequential is graph y1 and then graph y2. Mine does them together because I have it in that mode. So there's that. Now, if we really wanted to get a good look at what's going on in the neighborhood of this, I'm going to do a zoom box. Do you know how to do that? A Z box. It's kind of like a screenshot. So I would like to do it around the point 0, 1. This is the point 0 and a little bit more than 1 that I'm interested in. So I'm going to go a little bit up from that and a little bit over and hit enter. And then I just get to drag this little box around the part of my graph that I'm interested in. So you can see the tangent line is on top there and the curve is underneath. And as I move the cursor around, I can trace on the curve when x is equal to negative 0.1, for example. That's right around there. You can see the differences in the values there. You can see that they're very close. I could zoom in more. And then same thing. So it's just the same as like typing the things into your calculator like I did on numbers 1 and 2 to check to see how close. Now we're just checking sort of visually from the graph how close those values are. And they are as close as those two things look like they're close together. Right? They're close. Number 4, find a local linear approximation of the function 1 over the square root of x. That's the same as x to the negative 1/2. That's more calculus friendly, at x sub 0 equals 4. So f prime of x is equal to negative 1/2 x to the negative 3/2, and f prime of 4. Oh boy, testing my skills here, right? Can you do these kinds of things without calculator? So 4, the square root of 4, that's what this means on the bottom, is 2. Cubed is 8. The negative sign flips it over to 1/8, and then I'm multiplying by negative 1/2. Right? That is fair game to show up on a no calculator quiz or test, or the AP test. So got to know how to do that. And let's see, so I think I can write my, did I get my actual point? Not yet. So the point is 4 comma square root, flip it over, is that. So y equals my y coordinate. I'm just moving that over preemptively instead of having y minus 1/2. I know I'm going to want to move it over there. Sorry, the slope is negative 1/16 times x minus 4. There's my tangent line approximation. That's the main number one thing that I want you to be able to do here. So they want us to try this for 1 over the square root of 3.9. What's that approximately equal to? Well, that's approximately equal to 1/2 minus 1/16 times 3.9 minus 4. If you're thinking about this as the delta x, that's a delta x of negative 0.1. So negative 0.1 So if you're going all the way with no calculator, and then do you know what's going to happen here? Do you think you could blah, 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 and write the answer here? I bet you could. I mean, it's a linear approximation, so if we're wiggling the same amount on the other side, then it's going to wiggle the same amount on the other side from the 1/2, right? You could write out all the work. 1/2 minus 1/16 times 4.1. Sorry, I don't know why I closed those parentheses. Minus 4, and then that's just going to be plus 1/10, and so on and so on. Right? And then you can make the graph. I'm going to leave that for you to do on this one. All right. What's next? Number 19 to 27 odd. That sounds like 5 problems. 19. So use an appropriate local linear approximation to estimate the value of the given quantity. So we need to figure out here what function and what x value would make sense. But it's pretty easy to do. Like here I'm raising something that's close to 3 to the 4th power. So my function is x to the 4th. And my nice y value, or my nice x value rather, sorry, that's near this is 3. So I'm going to find the approximation for this at x equals 3. To do that, I need point and slope. So my point is 3, 81, and my slope is 3 plugged into this, which is 3 cubed, 108. I don't know, why do I have parentheses issues here? It's so what I want to say here is y prime of 3 equals 108. All right, so my tangent line approximation is y equals 81 plus 108 times x minus 3. That's like your delta x. My delta x is going to be 0.02, right? So what's the approximation? Y is equal to, and I think I'd like to say here that 3.02 to the 4th is approximately, this is the thing I'm approximating, right? It's going to be approximately equal to 81 plus 108 times 0.02. You want to have a debate with me about whether it's easier just to multiply this by itself 4 times by hand or to do this? Sure, I'm totally willing to be persuaded, but that's not the point. The point is that you can do this and it works. It gives you a good approximation. So there. And I'm not going to force you to simplify more than this. Although this wouldn't be that hard. We could do this by hand, right? So 108 times 2 is 216, but it's really 2.16. So that's because of the decimal. So 2.16, that's 83.16. Want to check real quick? Oh, my batteries are still low. 3.02 raised to the 4th power. 83.18. We got 0.16. Not too shabby. All right, 21. What's the square root of 65? You're like, what? That's maybe a little more obvious here, but think of something nice that you could take the square root of that's close to this. So if y was equal to the square root of x, and I picked x equals 64, that's a nice value. I can do nice stuff by hand. And y prime is equal to 1/2 x to the negative 1/2. So my point is x, comma 8, x, comma 8. 64, comma 8, and my slope, y prime of 64, is, well, let's see, 64, the square root of that is 8. That's what the 1/2 power means. The negative sign flips it over, 1/8 times 1/2 is 1/16. So my tangent line is y equals 8 plus 1/16 times x minus 64. right? And that means that the square root of 65 can be approximated by plugging 65 into this, which is 8 plus 1/16 times 1. Want to check? What's the square root of 65? What is 8 and 1/16? You know what I'm going to say. Not even going to say it. 23. I've already got, it's the same function, square root again. We want the square root of 80.9. And that's going to be y equals the square root of x again. Y prime equals 1/2 x to the negative 1/2. And we're going to make our tangent line at a nice value that's close to this and plays nice with this function. X equals 81. And y prime of 81 is plugging 81 into this. The square root of 81 is 9. Flip it over, multiply by 1/2. 1/18. And my point is 81, 9. So my tangent line is y equals 9 plus 1/18 times x minus 81, which means if you want to approximate the square root of 80.9, it's 9 plus 1/18 times this minus 81 is negative 0.1. So that's 9 minus 1/180. If you know how to do math, then you probably believe me that that's true. I could, I don't know, you want to try to simplify that like an 8? I guess that's 8 and 179 1/80ths. Sure, whatever, this is fine. I think that really captures the idea too. It's really close to 9, right? If you take the square root of 80.9, well, it's going to be really close to 9, and we're approximating that it's this much less. Want to check? What is the square root of 80.9? And what is 9 minus 1/180? Oh, wow, look at that. 25. What's the sign of 0.1? No, there's no little degree. If you look at 27, there's a little degree symbol there. So I guess that means we're in degrees. So if that's not there, we must be doing radians. And radians is good news for us because if you want to do calculus with trig functions, you need to be in radian mode. So I'd like to approximate the sine of 0.1, and that's pretty close to the sine of 0. So I guess obviously it's the sine function is my function. I'm going to do it at x equals 0. I'll make a tangent line. And I'll let you do the work here. I don't know if you remember this. We've seen a few times that the tangent line to the sine function at x equals 0 is the line y equals x. Well, that's kind of funny, because that means my approximator is that if you want to approximate the sine of 0.1, you plug 0.1 into this, so it's approximately 0.1. Huh. How about that? I mean, is that for real? Let's see. I'm going to make sure that I'm in radian mode. Must have been doing some physics. And so, I mean, 0.1, obviously that's the thing I'm comparing it to. So is the sine of 0.1 really like close to 0.1? It sure is. A little bit below. So yeah, it is, because, and that should make sense because if you look at the graphs of them, the graph of the sine function, I mean, its tangent line is y equals x. So it makes sense that in this neighborhood close to 0, the values of the sine function are actually just really close to the value that you put in, because it's right along that y equals x line. where y's are equal to x. Inputs are equal to outputs. Is that all we need to do for that one? Yeah. And then the last one, I just have a little bit of paper left here. So we got a tricky situation here. What's the cosine of 31 degrees? Well, the problem is, as I just stated, that you can't do calculus. If you want to be able to say, oh, the derivative of the cosine function is a negative sine, that's true, but only if you're in radian mode. So I need to switch this over to radian mode to be able to make this work. So instead of 31 degrees is the same as 31 pi over 180. Remember how to switch from radians to degrees and vice versa. So what's the nice value? The nice value is 30 over 180, or in other words, pi over 6. So the point here is pi over 6, comma, what's the cosine of pi over 6? Pi over 6, the cosine of that is the square root of 3 over 2. And then here, my y prime, my slope, is going to be negative 1/2, right? Because the sine of pi over 6 is 1/2. So my tangent line approximation is y minus, the slope is 1/2 times x x minus pi over 6. That's what we got. So what are we plugging into this? We're doing this, so the cosine of 31 pi over 180, which is the same as 31 degrees, is approximately equal to the square root of 3 over 2 minus 1/2 times, this is the delta x, so this is it's a pi over 180, bigger than this. Remember, this is the same as 30 pi over 180. You look at this and you're like, what kind of like lousy approximation is that? I mean, it might not be lousy in the sense of how close it is, but what the heck are you supposed to do with this? If the whole point of this is trying to be able to find nice approximations without using your calculator, this is not particularly helpful because, so I think that's kind of the point of this problem. That, you know, it depends how useful this is on the situation that you are in, but that is the approximation. Want to check? We checked all the other ones, might as well. So let's see. Let's go back to degree mode and do the problem as written. So what is the cosine of 31 degrees? It's that. And what is the square root of 3 over 2 minus, that's the same as pi over 360, right? Pi over 360. And there you go. I mean, it's a good approximation if you got that kind of money. All right, see you later.